Okay, so the next presentation will be by Axel Vierling, and for the article with the ID 35 progress estimation of an excavation bit.
Okay, hello. I hope you can see the presentation and can hear me fine. If not, just say so. So as already introduced, my name is Axel Vierling. I'm part of the Robotics Research Lab of the Department of Computer Science in the TU Kaiserslautern. And the topic is progress estimation of an excavation pit. But what does this really mean? So we don't want to estimate only the current progress with respect to the volume or the mass, but rather with respect to the performance or the current speed, how fast we are excavating. So because of course, the deeper the trench is, the longer we will take to do the next excavation step. Or for example, if the soil conditions are different, then we might take longer than at another part of the excavation pit. So we want to take this into account. So it's a progress estimation with respect to the performance or the speed. Okay, and now how did we do that? So in order to do this, we will shortly discuss the hardware setup as well as the software setup, then go to the point how the progress estimation with respect to the speed is done from a civil engineering point of view, and then we will check how to get this with our sensor data aligned, and then we'll shortly show some experiments and discuss the results. So from the hardware setup, the excavator or the backloader which we had was a John Deere 410J TMC. Here the special part, so to speak, is that it has joint encoders in each of the joints of the excavation arm. So we get our pose of the bucket, for example, from these encoders and don't need to add an IMU. However, we still have one IMU added in order to have the yaw as well as the current pose of the backhoe loader itself. We also have a RTK GPS or GNSS system to know the position. This is mainly used to know where we are with respect to our plan, because of course this excavation bit is usually beforehand planned and we want to excavate it with respect to this plan. The main sensors, however, which we used are the 3D laser scanner and the time of flight camera. They are mounted here on this robot or the excavator in the blue circle, which you can see. And this will be our main source of sensor information. From the software setup, what we used, so one of the main things is the control architecture. So in fact, in our robotic research lab, we have this excavator doing the excavation in an autonomous way. So the control architecture is one of the main points which we consider. Here the trenching is in fact divided into 4 phases: move to digging phase, move to dumping phase, and the dumping phase. And we will make use of when we know when we are in which of these phases. Then we also take into consideration the bucket estimation, which we also presented in another paper, and this just estimates the current fill level of the bucket as well as the overfill, so to just get an estimation of what is inside the bucket. And we take into consideration the rock size classification. Here, this what it usually does, it takes the depth map and tries with a watershed algorithm to estimate the size of each of the rocks. And then we can say how many big ones there are, smaller ones they are, and take this into consideration for the progress estimation. Sadly, in the experiments, this did not make any difference because where we were doing our experiments, there were no big rocks. So this is, had no effect in the later experimentation. And the last thing which we used is the 3D surface map. This is just more or less the sensor data of the 3D laser scanner put into a grid map. And of course, this is then dependent on the current position of the laser scanner during the excavation process and therefore also the boom. And what we can see is that the green points denote a higher value and the red ones denote a lower value. And this is what we want to use to really estimate what has been removed. Okay, so this kind of paints the picture of what we already have in our software and what we want to use. Now the question is, how can we use this to estimate the progress for such an excavation pit? And in civil engineering, there is also quite some work in this field. And these are the progress estimation parameters which are needed in order to calculate this performance. We'll go through them shortly. So the nominal bucket volume is just the volume of the empty bucket. Cycle time, just the time between 2 digging cycles. The dissolving factor is kind of the difference between the volume of the compacted and the loosened soil. The fill factor is how much of the bucket is filled with the things which we want to excavate, so sand and not, for example, air, because of the rocks in between. Trench depth is just the depth of the trench, rotation angle, the angle between the dumping position and the digging position. Maintenance is the current state of the machine, so how far along we are for the next maintenance step. teeth conditions, the condition of the teeth. Damping accuracy states how precise we need to be with the emptying. So is it just somewhere on the left? Is it a specific point? Is it maybe a truck? The operator is the skill of the operator. The operating conditions are, for example, the current weather conditions. This also affects, of course, how well the operator can work, and the machine utilization rate, which tells us how much of the time the excavator can really work on the excavation and does not maybe need to wait. So these are the general parameters for the progress estimation. However, we want to focus mainly on the things which we can compute from the point of the machine. And some of these, therefore, don't make so much sense. So, for example, the operating conditions and the machine utilization rate, this is dependent on the planning of the construction site as well as the current weather conditions. So we might not want to do this from the machine itself, maybe from some other sources. Similarly, the operator, of course, since we want to do an autonomous excavation, doesn't matter. The emptying accuracy is also always exactly 1 point. So this doesn't change. And the maintenance as well as the teeth condition is probably easier extracted, for example, from the software of the excavator manufacturer, who very often anyway have this already included, or from the construction company. So this also is much easier taken from some other sources. So this leaves us with these parameters, which we want to now really estimate in an automatic way from the excavator. Okay. So the nominal bucket volume, so just the volume of the empty bucket. So this we can directly get from the technical documentation. The cycle time, this is just the time between 2 digging cycles. This, of course, measuring time is relatively easy, and this we will do from the control, but all of these we'll also see shortly at an example. The dissolving factor is just the volume of the loose soil and the compact soil. So this we will get by computing just the volume of the loosened soil, so what we have in our bucket, and the volume of the compact soil, so to speak, what was removed from the ground. The fill factor is dependent on mainly the rock size. So here it's stated in the sources which I've given before that it's just 1 if there are no rocks smaller than 6 centimeters, or the average rock smaller than 6 centimeters, and then it reduces if the rocks are getting bigger. Like I said, sadly, where we did experiments, there were not many rocks above 6 centimeter diameter. So this is in the experimentations kind of omitted. Trench depth, also, calculating the trench depth is not so difficult in principle. We just need to know when to do that. Similarly, for the rotation angle, that's also mainly dependent on getting the poses at the correct time. So let's take a look how this looks for the actual excavator. So we'll here see on the bottom right the autonomous excavation with a speed of 1.5. And we see here on the top left the current activity or behavior. So currently we are in the digging cycle, then we will go to the transport to dumping, go to the dumping, and then move back to the digging start. And of course, we can know then when the next behavior gets active, and therefore we can directly deduce the cycle time by just checking when the second time the digging is active. Similarly, since we know the dumping position and the digging position, we can directly deduce the current rotation angle once these behaviors get active. Also, we can directly compute the trenching depth if we know the correct position in time. That is then when the digging cycle ends and we start moving to the dumping phase. So once digging is over, this is the lowest point. Next thing which we want to know is the volume of the loosened soil. So this is just the volume of what is inside of the bucket. So here we have an empty map of the bucket, and we have the measured map from the time of flight camera where the sensor data is seen on the right. And now we want to compute this difference in this difference map, but only once the bucket is at a suitable angle, because only then we can also really measure something. So we then compute the difference between the empty and the measurement map, and with this we can estimate the volume of the soil, which we then just save during the transport to dumping phase, because that's where the bucket is mainly loaded. Then the next thing is the volume of the compact soil. So for this we take the data of the laser scanner with the 3D surface map, which we see here. So we see here the 2 cycles for the digging and the dumping position, and we see here on the local target map the planned state, and we just calculate the difference between 2 digging cycles for the planned excavation pit. And then with the grid map, we can then relatively easy calculate the change and then get an estimation what has been removed from the ground during one of the digging cycles. And then in the end, these are the parameters which we wanted to calculate and what we needed. And this is an example of how it has been calculated for one example now. Yeah, so some more can be seen in the paper. However, yeah, I think one is fine due to time constraints. So how were the results in total? When we checked most of the cycles for the digging, the results were meaningful. They were in suitable ranges, and it also seemed to correlate with the progress which we wanted to have. Some problems still were present from the methodology. So one of the main problems is that during the excavation, the soil can break from the sides again back into the pit. And this is somewhat difficult to see or to calculate then where it changes. So we did this we tried to solve this by just not taking the grid cells of the exact target pit, but also the neighboring grid cells. This improved things, but still this is a little bit of a, let's say a weaker point of this methodology. So also, of course, we only consider the loosened value in the bucket, but not while, for example, loading into a truck, right? Again, becomes even more loose. And some implementation things which we could have improved is that we sometimes, due to losing our GNSS signal, we lost we had miscalculations in the trenching depth. Here also some reviewers commented that we could just do this by some ICP algorithm to get a better local post estimation. But here, the main problem was that we wanted to be relative to our planned pit in the beginning. And this is where here some problems came into play. However, for example, one very nice side effect from all of these calculations for the progress estimation is that we could then also correlate our speed with the speed of, for example, a proficient excavator user. And this autonomous excavation achieved a speed of roughly 60% of what such a proficient excavator user would have achieved, while, for example, an amateur achieves 65%. So this directly gives us a nice measure of how well our excavation algorithm works. These are here then the sources, and in principle, that's then it from my side, and I am open for some questions.
Okay, thank you so much, Axel. We have a question in the chat.
So I see.
I can read it if
yes,
you
okay.
allow me. So the question is from Rose Worker. The question is, how are the interfacing with the machine? If so, did Deere provide the message?
So not directly. So they included communication auto box, they call it, so that we don't directly have access to the CAN interfaces due to some let's say safety NDA reasons for them. And so we just have this intermediate box where we have access to some of the commands, which are then by a gateway, so to speak, brought to the actual CAN interface.
Okay. Thank you. A question in my mind, what can be future development for this work, and how the efficiency can be improved, if what are the solutions to improve the efficiency?
Okay, so the idea behind the usage of this is more in the direction actually of having an estimation how good the current construction site is working. So to have an estimate how correct we are with our planning. That was also what this was done for, and then also in the scope of the project used further for. And then they checked and compared the estimated progress with the actual one to see if we are still on track for the changes in the construction site. So to prevent some delays, for example, during the construction, or to notice them very early on. Regarding the improvement of the accuracy, so I think this is mainly that we might need to have some more estimations in between of the grid map, because this was the main problem. And so that we can maybe detect also when the sand is falling down, and then take this into consideration more, and maybe have some special calculations only for this case. Because as I said, this is kind of the major backdraw currently, or major problem.
Thanks so much. Any other question? Okay, thank you.